Okay, so let's talk a little bit about some other non-ideal effects in a p-n junction. So we'll start out with a junction recombination and start deriving some expressions that hopefully make sense to you. So here we are. Let's take a p-n junction under bias as sketched here, and we'll write down again the mass action in non-equilibrium. We had written this down before. This is just a reminder. That means the product of n and p in this non-equilibrium condition is no longer just ni squared, but it's proportional to the exponent of the applied voltage, which translates into the difference between two quasi-Fermi levels, for an electron quasi-Fermi level and the whole quasi-Fermi level. All right, so that being said, we can use this expression for a little bit of work. Just as a reminder, what's a recombination process? So you started with an electron and a hole, and they recombine and destroy each other. We've gone through that at quite some detail. And you remember this pretty horrendous looking expression for the Shockley-Reed-Hall equation that describes the recombination via traps. And in order to get the trap current or the recombination current, we integrate the total amount of decay of these electrons via the Shockley-Reed-Hall expression. And we integrate the decay over the depletion region here. Okay? So let's make a couple of assumptions to make our life easier. Let's assume, for simplicity's sake, that the minority carrier lifetimes are identical and that we deal with traps that are at mid-gap or at the intrinsic level here. That means that N1, P1 are Ni. So that makes this expression we have up here more palatable. We basically plug in N times P here, and we find Ni squared and the exponential minus 1. We are setting the taus to be identical, and then we have the tau over here, and nx plus px plus 2ni. All right, so that's a more palatable expression. And again, what this indicates is that there's a recombination in the depletion region that is significant as you crank up a voltage, okay? Because you're creating a significant charge imbalance from the equilibrium values. So there shall be, given that there are traps and a finite relaxation time tau that brings in the traps, there shall be some sort of relaxation. Now, if the minority carrier lifetime were infinity, tau towards infinity, right? No relaxation, that means this relaxation term would be 0. So if we didn't have traps, then tau would be infinity, then delta n dt would be 0, the recombination would be 0. Okay. All right. Now, as before, you can write down the intrinsic energy level in the system as part of the equilibrium on the left, and add the applied electrostatic field to it, like this. And you can then plug this expression of EI into the expression for n over here, and calculate an electron density throughout the device. Now, in the majority carrier region, so in the n-doped region, n is approximately nd, right? The doping, so it's flat. And as this distance here between the Fermi level and the intrinsic level, sorry, you have a exponentially decaying number of electrons in the system. So you end up with a curve like this. Okay. Same you can do also for holes, but now you express the holes as n times p equals ni squared e to the q va over kt, like this. And P is this whole thing divided by n, okay? So we'll just carry this expression over here, and you then multiply through with the exponent, and you have an expression like this. You have a symmetric expression. You have constant donors, holes, according to the acceptors on the p side, and you have an exponentially decaying number of holes throughout the rest of the device. All right, now let's see what we can do with this for junction recombination. We want to evaluate this expression, and we want to make our life a little bit easier, introduce some, say, helper coordinates, where we introduce a potential U that is now normalized by KT. And we'll do this for the applied voltage as well. And we rewrite the expression for the relaxation rate here in terms of these U's. Okay? So nothing really fancy going on so far. But what I'll do is I'll pull out this term UA over 2 out of the exponent on the top. Okay? And I see something appear that begins to look familiar if you're familiar with additions and subtractions of complex exponentials. Complex exponentials would be sines and cosines. Decaying exponentials are hyperbolic sines and hyperbolic cosines. So we can basically reformulate these expressions in the form of hyperbolic sines and cosines. All right, and then ultimately we want to integrate the expression for delta n over the depletion region here, right? Good. Now, we only need to keep the terms that are dependent on x in the expression, and that is our term u here. So the hyperbolic cosine under the hood stays in the integral. And we'll start trying to solve this integral, okay? Now, one approximation, and again, keep in mind this comes from sort of the 50s, people not having significant compute resources, and they try to get, again, analytical insight. One step you can do is you can just keep the positive branch of this hyperbolic cosine, okay? So you approximate that with just the positive branch and delete the negative branch in the hyperbolic cosine. Then you can make an approximation that you, instead of having an electric field that is really spatially varying, you can clip it to some max value and assume that it's constant inside. So if you do that, you can come up with an expression for the junctional recombination and forward bias, okay? And that's the expression, and notice the exponent of 2, or 1/2 in this case. This expression here, the component here, corresponds to a effective spatial width, and the excess carriers at mid-junction with a factor of 1/2 indicates that you have recombination due to traps, and the traps are hidden here in this tau. Okay, so that's the lifetime, the traps, the properties of the traps. So if you're a p-n junction behaves with this factor of 1/2, you know that down here in this region you have traps in your in the depletion region, and you need to do something more about the quality of your p-n junction. Now, there's junction design considerations. You know of the corner effect if you studied electrostatics. It's a typical effect where you, if you have two plate capacitors, right, you have electric fields that run very parallel. If you have a point, then all your electric field lines are coming to the point, and you have a strong electric field coinciding on strong points or corners. The same is true when you have real p-n junctions that are in planar design. You might have designed a junction with this kind of design in mind, where you might have a linear cut through in mind, as we had sketched in the beginning of these segments. But in 3 dimensions, you really have more complicated corners, and you have a corner effect, and you might have to do something to get a better performance in your recombination. All right, now let's look at the depletion, in the reverse bias, and let's look at a structure where we have now reverse bias and a pretty large depletion width. We had sketched that as you apply a stronger bias, you pull apart the depletion regions even further. Let's remind ourselves again of this glorious Shockley-Reed-Hall expression that is pretty long, and we'll do the same approximation of what we just did a minute or two ago. We assume that the taus are identical, traps are mid-gap, N1 and P1 are then at mid-gap, meaning Ni, and we have an expression just like what we just had written down. Now, if I'm at a negative bias, you can see that this term is negligibly small, okay? And you end up with it, and you can neglect these n's, and you basically end up with Ni over 2 tau, okay? So here we are. We have a recombination in the depletion region, which is something we had calculated before. And we had calculated before, if you have a depletion region like this, and you have a constant recombination rate, you end up having an expression like this, where the current is now proportional to your depletion region width, okay? And we know that we had written down that this width here is proportional to some VBI minus VA, just like here, okay? So that now means that your current is dependent on the depletion width, and therefore with a voltage, and it goes as a square root, okay? So instead of having a flat voltage independent reverse current, you have more current flowing that goes with a square root of the voltage. So again, this is another mechanism to probe for traps in the junction. All right. So we talked about junction recombination. Next step is we're going to talk about tunneling. Now, here's a so-called Esaki diode. Esaki was the person that really explained this well and had some insight. And what he did is he not only sketched this into a notebook like Nice did a couple of years before him, but he actually measured this. Now, this Esaki tunnel diode behavior only occurs if you have a very heavily doped diode. So here's a diode sketch in equilibrium that looks a little different from what we had seen before. These are now degenerately doped diodes. So the Fermi level is actually above the conduction band edge, and the Fermi level for holes is below the valence band edge. And notice that the built-in potential now is actually larger than the gap. So early on we postulated maybe that's the biggest built-in potential you can come up with. But if you actually have very heavy doping devices, you can build in a potential that is larger than the gap. Now, if you compare this kind of behavior to the traditional IV of a perfect diffusion-limited PN junction, that is a perfect exponential, and you begin to apply a voltage, you find that there's some strange behavior. The current goes up, and it then goes down, and then begins to follow the normal IV characteristics of the device. So where does this come from? You can sketch it like this. So you're going in forward bias, you're raising up the quasi-Fermi level for the electrons, and what you're finding is that on the P side now, you have empty states, and electrons will start to tunnel through this device, and current grows more than it would have grown if the electrons were going over here as diffusion injected. Now, if you increase the voltage further, eventually you hit a point where this sea of electrons does not have empty states available on the P side. So then there's no more injection, and then the device begins to just behave like a normal diode where you inject minority carriers on this side. Okay? So that's a so-called Esaki diode, and Leo Esaki got a Nobel Prize for that, because it really revealed that indeed a band gap exists and you can tunnel across a band gap. And this was a significant discovery in the field of semiconductor devices. All right, so if you do this in reverse, heavily biased device, or actually any device, PN junction can do this under a strong reverse bias. What happens is you uncover empty states here, and electrons can tunnel over here this way, and they have empty states. So you have full bands here, so the electrons are occupying states, but they can tunnel over through the barriers into empty states. Now, if you increase the bias further, you'll have more tunneling current as you expose more states. Also, you narrow the tunneling barrier. And you can visualize it like this. Effectively, these electrons start to see a triangular tunneling barrier. And you can calculate that explicitly, and you might have read that in your textbook, or you might have done an exercise where you calculated that tunneling. As you increase a higher bias, this triangular barrier becomes narrower, and therefore it increases the tunneling. So this tunneling through a triangular barrier you can carry through. There's an example in your textbook, or you can calculate that as a homework exercise. All right. So we've made it through pretty much all of the various regions of the IV characteristics. And let me begin to summarize that these different slopes that we identified, 1/2 here, 1 and 2, and the square root behavior like this, are indications for the quality of your device. How many traps do you have? How high is your doping? And it allows you to characterize your device. So again, when you run new measurements on new devices, people will ask you, what is your ideality factor of your IV characteristic? And those would be these exponents people refer to. Now, of course, you can calculate all of these things numerically now with engines that have these processes built in, but you still end up finding that these exponentials really are meaningful, and they allow you to get a full understanding of what is going on in the device that a pure numerical calculation would not reveal. So with that, I thank you very much for your attention. Okay, so we just talked about tunneling. Let me talk about impact ionization now. All right, and that's really talking about breakdown in the realistic structure and avalanche breakdown. All right, so if you have a junction in reverse bias, you might have some electrons that are still around even in the reverse bias configuration, and they might sort of trickle down and interact with phonons and lose their energy that way. Okay, so that would be a reverse bias flow of electrons. Now imagine that you have a really high bias applied to your device. And somehow you have this stray electron that is up here. And let's say it has an energy that is typically 3/2 the band gap. Let's assume that it actually travels over here and gains a lot of kinetic energy. So as it generates or gains a bunch of kinetic energy, it can actually kick up an electron that sits down here, kick up and generate another electron. Okay? And it generates a hole that can then flow this way. These two electrons now can travel forward, gain a bunch of energy, fall down, and each generate 4 more electrons. Well, each 2 more, meaning now we have 2 holes here that will travel forward. Okay, so you're going from 1 to 2 to 4, plus you go 1 to 2 on holes. Now imagine this keeps going. You go here to 8 and here to 4. Okay? So you have an avalanche effect that given enough energy, these electrons can excite other electrons from the valence band into the conduction band, create more electrons, and they can create more holes that can also then impact ionize. So that's an exponential growth, and it's called impact ionization, and ultimately it leads to a breakdown of a junction. Okay. Now here's an animation of this where the carriers basically start to multiply. Okay. Good. So can we calculate this? Now, here's an empirical ansatz to the problem where we say, well, the current at a space x plus delta x is dependent on the original current plus some current that is generated within the distance delta x due to impact ionization. There's some coefficients alpha n and alpha p that identify or scale the probabilities of such impact ionization to happen. And these terms can then grow exponentially along the device. Okay, so you can build a differential of this, and you end up with a differential equation that looks like this. All right, so far nothing really fancy going on. One thing that we're going to simplify things with, at steady state, the total current is the sum of the electron current and the hole current that is being generated in this impact ionization. So we're going to write it like this, where we can substitute the hole current by an expression of the electron current. Okay? Again, nothing fancy here. And what we're going to do is now bring the total current to the right-hand side, and are left with a differential equation like this. Okay. Now we can solve this differential equation, and this looks a little bit like a y prime minus ay equals b. The general solution to that integral looks like this. the non-definite integral like this, except now these alphas here and INs are functions of x. So it gets a little bit more complicated. So the true solution to the differential equation includes these double complex integrals. And we'll need to introduce a couple of approximations to this solution. Okay, so first of all, we'll assume that the current up here, the initial little trigger of an electron flow into the system is negligibly small, certainly compared to the final current that is flowing after the avalanche happens. Okay? So that's assumption number one. And then we assume that down here at the hole side, at the end of the depletion region there, that also the initial hole current is zero. So everything is really generated inside of the depletion region like this. So we had said that the total current is the electron current plus the hole current. If we evaluate the total current, which is continuous in the different slices, just here at this region W, we can say that the total current is approximately to the electron current that is being generated through avalanching. Total electron avalanche current at this site W. Okay? And we introduce a factor, it's called the multiplication factor. That's how many more times total current do you get out compared to the electron current you stuck in here. Okay. So far we actually haven't done this approximation here. Okay. All right, so now I'm plugging in these coefficients into this horrendous looking exponential integral, and it looks pretty horrendous still. Let me see what other approximations I can do. So first of all, I'm just multiplying out the denominator all across. And I can see that I cancel a couple of terms over here. And I am bringing, so here's this 1, right? This guy turns to be 1. That's the 1 here. That's the 1 here. I'm bringing the 1 over, or I bring the 1 minus 1 over m over. All right. Now, I'm assuming that the multiplication is so tremendously large that I can neglect this term. So I call this 1. So now we're stuck with still a pretty complicated integral having the value of 1. Next, we're going to assume that alpha n equals alpha p, that the avalanche generation probability for the two carriers is the same. Can't be quite right, because electrons are lighter than the holes. They should be generating other electrons easier, but we'll assume it anyways. If that's the case, then you lose this horrendous exponential up there, and we don't need to integrate over the details of this alpha n and alpha p as a function of x. Okay, so not the complex exponential here. Now the next assumption is we actually assume that this coefficient is constant throughout the junction. And the key element to understand is that most avalanche happens roughly in the middle of the junction, because that's where the electric field is really the largest. So if we assume that, then alpha n times w turns 1. And there's a bunch of experimental evidence and a bunch of theory where faculty have spent loads of their research time trying to figure out what these avalanche probability coefficients are. So there's an abundance of research on this, where you can look this up in publications, in textbooks, and you can then relate this avalanche to a particular breakdown field. And given a certain, if you reach this breakdown field, you can then expect avalanche to happen in reverse bias devices. All right, so this impact ionization can be a pretty bad thing, or it can be very good. Now imagine in the good circumstance where you have an electron maybe about ready to be injected there. Maybe it's a single photon that you can absorb by generating exactly one electron-hole pair, but you generate it right teeter-tottering, where if this electron falls, it will multiply into many electrons, and you can measure that. Now that's a avalanche photodetector. So that's a very cool thing to utilize this avalanche effect. Now, there can be bad things if you're, again, in a realistic device and you have stray fields on corners where the electric fields are much larger than you expected them to be, and you can lead to breakdown. So now this can lead to some engineering solutions that you may be pursuing, where you want to reduce the electric field at a particular junction. And this can be done, for example, by inserting between the P and the N region, inserting an intrinsic region, an I region. And what that does is it effectively clips the maximum amplitude of the electric field and spreads out the electric field in space, because the total area under this curve will be the same in this kind of design. But you've clipped the maximum electric field. And the area is the same because the VBI is the same that you built into the device, because that's again just determined by the doping of the P and the N region. So by inserting a thin layer here that might be intrinsically doped, you can cut down on the peak electric fields. And that was a pretty important design feature for MOSFETs, where they needed to reduce the fields on the drain side to increase the reliability of these devices. All right. Finally, there's an aspect of something called dead space. In today's devices that are extremely small, extremely short, where this width may be very small, electrons may never actually scatter inside the device. They might actually reach the other device and before they have a chance to avalanche. So you might have ballistic junctions where the electrons shoot straight through without inducing impact ionization. And the lingo here is the dead space that will allow the electron to really accelerate is too small in order for impact ionization to happen. Okay, we're going to close down now with a discussion on how to distinguish Zener breakdown versus impact ionization, because they're similar effects, right? You have the avalanching here, and you could have Zener tunneling and reverse bias. How do you distinguish between these two? Well, you can do so by a couple of different measurements. Number one, for impact ionization to happen, you need to have a bias that is at least larger than the band gap. Otherwise, you don't have carriers that can generate as much energy as need to cause avalanching, okay? So for impact ionization, you need bias. So if you have a breakdown, a Zener breakdown for a device that is close to 1 eV, when your band gap is roughly 1 eV, then you must have Zener breakdown rather than avalanche breakdown. Now, so this means the Zener tunneling can happen for relatively small reverse biases. Now, there's another aspect to the impact ionization, that is the noise behavior of the device. Now, if you generate all these carriers by impact ionization, this is a very noisy behavior, and you can measure that in your signal, in your time variant behavior of the electronics. So it's very noisy versus the Zener tunneling is relatively smooth compared to that. All right, so I think we're reaching the end of this section. The junction recombination is often used to diagnose processes in devices and diagnose the maturity of a device. These defects in junctions can be misplaced donor or acceptors. They may not be from deep traps. It's just the thermodynamics of implants or etc. might have not had the donors settle into the appropriate crystal places and create trap states instead. And impact ionization plays an important role in a wide variety of devices like photodiodes, for example, or needs to be avoided at corner effects on three-dimensional geometries. All right, I think this is it for section 20, so I thank you very much for your attention.